Okay. Good afternoon, everyone. Welcome to the International Methods Colloquium. My name is Justin Essery. I'm an associate professor of politics and international affairs here at Wake Forest University. The International Methods Colloquium is a periodic online interactive seminar discussion on the application of quantitative statistical methodology to the social sciences, sponsored by Wake Forest University and by Springer Publishing. This week's speaker is Andy Eggers from the University of Chicago, but I think you're actually you're still in Oxford right now.
That's right.
Giving a talk entitled Placebo Tests for Causal Inference, and as you can see, that's joint work with Alan Defoe and Guadalupe Tunon. I apologize if I pronounced either of those names incorrectly. Andy's talk will last for about 30 to 40 minutes, after which point we will take questions from the audience. You can ask a question using the Zoom Q&A button that appears at the bottom of your webinar window, and you can ask questions at any time during the talk, but all questions will be held until the end of the presentation. If you wish to be recognized and ask your question via audio, please indicate this in the Q&A text box. Otherwise, I will read your question aloud during the Q&A period. A link to Andy's slides will be available in the Zoom webinar chat window so that you can refer to it throughout the presentation. And now I'd like to welcome Andy Eggers to the IMC. Welcome, Andy.
Thanks a lot, Justin, for having me. Thanks, everyone, for attending. And I think Alan and Guadalupe are possibly in the audience, so if there's some way for them to, they don't have to chime in if they don't want, but
I'll promote them to presenters so they can if they want.
Great. Excellent. Great, so thanks very much. I'll just get right into it. So I'll start with a story about the way I encountered placebo tests. I think the first placebo test I saw was a response to a very high profile paper from, I think, 2007. I'm just showing the beginning of the abstract here, about examining the possibility that obesity might spread through a network through peer-to-peer sort of effects, like your friend becomes fatter and it sort of makes you fatter. Now, of course, these authors, Christakis and Fowler, were aware that when you study network data and you look at people becoming more and less obese in a network, there could be environmental factors that are causing two people connected to a network to become more obese. There could be homophily that causes people who are inclined to become more obese to be friends, et cetera. There's all these sorts of things, but they claimed that having adjusted for various things, they'd shown some evidence of a network effect. And the placebo test that I encountered when I was in grad school was this response, which says, basically, if you apply the same kinds of methods to the same data, you find network effects for outcomes where network effects are not really plausible, where homophily and environmental factors certainly could cause people who are friends to both be taller or to both have acne or something, but that for these particular outcomes, it would not really be plausible to say that there are network effects. And so the finding that if you use these same methods, you find some network effects suggests that there's some shortcomings in the original analysis. Now, I'm not an expert in this area. I'm not really here to say whether they've really convincingly shown this, but I found it sort of as a logical move to say, all right, let's reproduce the analysis as closely as possible, but tweaking one little thing where we think the main theory would be inert, essentially, where in this case, network effects would be operating. But some of the threats to inference would still be operating. And and in doing that replication with that small tweak, we get to kind of evaluate the assumptions and the validity of the original analysis. And I found that really a really compelling move. And so if you go back in our discipline, this is in epidemiology, but if you look back in our discipline, although obviously the fellows, political scientists, if you look in our discipline, at the time this paper was published, there's basically no placebo tests in political science. This is something we did for this paper where we looked at how often you encounter these search terms in leading political science journals over the past couple decades. And essentially nobody was doing anything that they called a placebo test at that time. But since then, it's really skyrocketed. So you see a lot in papers now. So something like 1 in 20 papers that has the word test in it has the phrase placebo test or some related phrase in it. So they've really taken off. And what we're trying to do in this paper is to try to kind of bring some sense to this practice of placebo testing, to try to provide a framework to understand how they are designed, what kind of sense they make, that both kind of helps people understand the tests that you encounter in literature and possibly helps you to design your own. So these are the kinds of questions we hope that you have in your mind. If you don't have these questions in your mind, you might not like the rest of the talk, because this is the kind of thing that we'll be talking about. So to start with the basics, what is a placebo test? Well, a placebo test should be put in the category of auxiliary analysis. So we would say, along with subgroup analysis that you might do to sort of see if the treatment effect is larger where you'd expect it to be larger if your causal theory is correct. Robustness tests, you kind of vary the design to see if choices that you made had some kind of outsized influence on the result. And sensitivity analysis where, like, well, suppose there was a confounder, how strong would it have to be to get a different result? So there's something that you do after the main analysis to assess, to provide some perspective on how our beliefs should be affected by that analysis, or how credible analysis is, you could say. Mainly placebo tests, as practiced in political science anyway, are tests, we can see them as tests for bias in observational studies where we're trying to understand effects, causal effects. And in that context, I think it's useful to think about placebo testing as a type of theory testing. So I think the kind of causal inference subfield has a kind of a reputation for being like theoryless, like that we're just out there, measuring effects of, or trying to estimate parameters without any kind of reference to any sort of theory. But I think if you think in the broader sense, placebo testing is a little like a microcosm of what we think of as bigger kind of theory testing. So what I mean by that is we see an association in the data, and to call that association the residue of a causal effect is a kind of theory of how it came about. And so say, this association is a causal relationship. The X and Y are related because X causes X affects Y, not because some other thing. And so what we're doing in placebo testing for bias, at least, is I think we're looking for a particular kind of telltale association that would be absent if the causal interpretation of the main finding is correct. So if the theory that you have about the causal theory that you have about this association between X and Y is correct, then we shouldn't expect to see this other association, but we should expect to see that association if some other interpretation is correct. So for example, if we think, oh, that actually X and Y are related because of some confounder. So I think it's kind of, it's useful to think about this as a place where we can do kind of relatively clear theory testing compared to trying to test very grand theories of politics. This is kind of small scale, but it's actually relatively logically pure. And I at least like that aspect of it. Now, although in principle there may be lots of different ways to do placebo testing, in practice there's a pretty simple set of things that people do to make placebo tests. So the general feature is that they minimally alter the core analysis. Core analysis is what I'm calling the main research design. So you take the main research design and you tweak something, just like in that first example I gave of obesity spreading in a social network. There you kind of just tweak which variable you're looking at, headaches instead of obesity. And that's a general feature. So placebo tests tend to be some minimal alteration of the core analysis. And we offer a typology that's based on which element is altered. So you can alter the population of the sample. So meaning like we're going to take the analysis that you did in this setting and we're going to do it in some other setting, or that I did in one setting and I'm going to do it in some other setting to prove to you that it worked. We call that a placebo population test. You go, if you alter the outcome variable, placebo outcome test. If you alter the treatment variable, placebo treatment test. So we find this typology to be useful to kind of get your head around what are the key features that a test has. The common logic that works with, at least for placebo, I think beyond placebo tested bias, so all placebo tests, is that you do this alteration in order to shut down the kind of purported treatment effect, but in a way, this is the tricky part, it's easy to shut down the purported treatment effect. You could just replace the treatment with noise or the outcome with noise, then you know that the treatment's not affecting the outcome. The crucial thing is to alter the analysis in a way that gets rid of that treatment effect while retaining some postulated flaw in the core analysis. So for example, you want some confounder to be present in the placebo analysis that you think might be present in the placebo in the core analysis that you want to deal with. You kind of shut down this one piece so that ideally all that's left is this flaw or this bias that you're concerned about. And I'll refer to these later, so I just want to set out some criteria for evaluating a placebo test for bias. What I mean, and you should read that as a placebo test for bias. How should we evaluate it? What criteria should we use? So the basic thing is we're going to call it a placebo test informative if its result would affect your beliefs about bias in the core analysis. So that's a big general idea. If we sort of simplify things a bit by thinking about a kind of binary null hypothesis significance testing framework where it's like accept, reject kind of result. We're going to reject the null or not. And also kind of binary in terms of what the alternative hypothesis might be. Then a placebo test is informative if it rejects the null with high probability when the core analysis is biased, which you could call high power, and with low probability when the core analysis is unbiased. So you could call that small size or low false positive rate. Now, as with any estimate, you can think about the estimate in the placebo analysis as being notionally composed of these three elements: the effect of the treatment on the outcome in the placebo analysis, the bias that is the part of the systematic association that's not characterized by the effect, and then some noise that's just random across hypothetical samples. Ideally, what you want in a placebo test is for that effect thing to be shut down, that effect thing to be zero, the bias component to mirror the bias in the core analysis. So you've made an alteration that gets rid of that effect, keeps the bias, and then has the noise be small. And we can think of these components. Obviously, if the noise is really big, if your placebo test is just super super noisy, then it's not going to have high power no matter to what degree it picks up some bias that might have been in the core analysis. If it's very noisy, it's not going to be a powerful test. If it retains some of the effect component, if you haven't really killed that effect component, the blue component, then you are probably going to have a high false positive rate. That's another. So this is how we're going to use that concept. To talk about placebo tests, I will be referring to a running example that we use in the paper. We choose this example because it uses an unusual number and variety of placebo tests. The paper is not perfect, and I'll say some critical things about it, but it's really impressive in this respect. So the research question in this paper is, how did pro-Russian TV that was broadcast into Ukraine in advance of the 2014 election in Ukraine affect voting and attitudes in Ukraine? So here's the map that they provide in this paper. So the sort of reddish, orangish dots here, or squares here, these are like voting, I think these are voting precincts in Ukraine. The triangles represent transmitters that are in Russia. So this is the northeast part of Ukraine where it's right on the Russian border, and this was a very contested time in Ukrainian-Russian relations. So these transmitters are broadcasting Russian news and other kinds of Russian TV. And over in Ukraine, you can access it to varying degrees in different places, depending on how far you are from a transmitter, and also depending to some extent on the geography between the place you are and that transmitter, so mountains and stuff like that. So to represent both the kind of concerns that we might have about this paper and how placebo tests will address those concerns, I'm going to use directed acyclic graph, DAG. I'm not going to get into this in detail. It's pretty intuitive, and I'm only going to use it in a pretty simple way. The idea here is that they want to understand the effect in some of the analysis of Russian TV signal quality, which is a feature that varies across precincts in Ukraine, on the degree of pro-Russian voting, let's say. There's a bunch of different outcomes, but let's just focus on that one. And that effect is captured by this arrow that's running from T to Y. That's what we want to measure. But we would be concerned maybe about some confounders. So it could be that places in Ukraine vary in their Russianness. So there's a lot of Russian speakers especially in this part of Ukraine. And it could be that people who are sort of more Russian anyway would be more pro-Russian in their voting for sort of cultural reasons and other factors. And also that could be that the TV signal quality depends on the Russianness of the place. This could be for various reasons. It could be that there's kind of strategic tower placement, for example, that towers are placed in places in Russia where they think they can reach kind of Russian communities in Ukraine. It could be that the mountains historically that lie between Ukraine and Russia, that mountains affected historical migration patterns, and then this affects, the mountains affect the signal quality, and then that affects the, and the mountains affect the Russianness, and et cetera. You can see how this works. Now, the way that we can use these DAGs beyond just drawing a lot of arrows is that if we make some assumption, if we assume that the variables are standardized, unit variance and mean zero, and assume that these relationships are linear, then we can express the association or the regression of y on t in terms of these path coefficients. So regressing y on t gives you a plus bc in this case. And bc is that bias we were worried about. Now, I want to clarify that they don't just regress y on t. They have control variables and stuff. And so you might want to draw the DAG in a more complicated way with controls and extra confounders and stuff. But just to keep things simple, we're going to just have treatment outcome confounder and suppose that that's the problem. Okay, so there are 3 types of placebo tests, and I'm going to show you how those authors use these placebo tests to address that concern about confounding. And then we'll try to talk about some more general questions about each of these types of tests. So a placebo population test is the simplest one. The idea here is that you reproduce the core analysis in some sample or population in which that postulated flaw or bias would operate in a similar way, but the treatment effect would not operate. So to illustrate that with these DAGs, you see on the left here, this is the DAG I just showed you, where there's kind of this main effect A that you want to be measuring, but there's this confounding BC that you're worried about. So what you want to do is, with the placebo population test, you want to find some population in which this treatment effect, the blue arrow, is sort of shut down, but there's a kind of similar type of confounding going on. So here I've written B prime and C prime next to these 2 arrows. The estimate, if you regress y on t, and if these are linear and standardized variables and everything, the regression of y on t gives you an expectation B prime C prime. And what you wanted in the first place was BC. Because what you're trying to track is you're trying to figure out how much was there bias in the initial in the core analysis, and you're doing it with this placebo analysis over here. So that's the idea. Let's see how they actually implement it. Well, the way that they do it is they do some separate analysis on the individual level between people who have terrestrial TVs and people who have satellite TVs or no TVs. So why does this make sense? Well, these transmitters that are in Russia that we're using as the treatment, the signal quality from these transmitters, could only really affect the TV viewing habits of people who have terrestrial TVs. It's not going to affect someone who has a satellite TV is not going to be watching Russian TV news. The idea is that he's not going to be more likely to watch Russian TV news because of better or worse signal quality from these transmitters, these sort of terrestrial transmitters, because this person has satellite TV, and that shouldn't matter for this person. So for this subset of people, the people who have satellite TVs, we would expect that the signal quality as measured with these transmitters is not going to affect how they vote. So that's the way we shut down the treatment effect. Now, as I said before, what you want is you want the postulated flaw, the bias, to be held constant between these 2 populations. So what that means in this case, you want B prime C prime to be something like BC. What you don't want is that, for example, that B prime is 0 in the placebo population over here. So Russianness doesn't affect TV signal quality for people who have satellite TVs, or it's not associated with TV signal quality for people who have satellite TVs. And so this is not guaranteed, right? You could have a clever way of turning off the treatment effect, such as focusing on people with satellite TVs instead of terrestrial TVs. But there's no guarantee that the people who have satellite TVs are actually comparable in the way that you want to people who have terrestrial TVs. So how could that be? Well, it could be that people who have satellite TVs, for example, they're richer, and they are mobile in a way that people who have terrestrial TVs are not. And so the pattern of settlement that relates their kind of intrinsic Russianness to where they end up settling might be different for people who have satellite TVs. So we might think that this B prime thing might not be similar at all among people who have satellite TVs and people who have terrestrial TVs. So that's and how would you know? Well, this is where kind of substantive knowledge and theory and stuff would make a difference. And this is true of all placebo tests at some level. There's no guarantee that when you've altered the core analysis to make your placebo test, there's no guarantee that the flaw that you're hoping to pick up on is actually operating in the way that you kind of hope. You certainly will never know that B prime C prime equals BC. If you did know that B prime C prime equals BC, you could just subtract the two effects and you would know that you have an unbiased estimator of A by taking that sort of diff and diff. But the idea with the placebo test is that you might not know that B prime C prime equals BC, but you might think that they're kind of similar enough that you think you might be able to test in the placebo population whether something like BC is close to zero. You can also use placebo population tests as a test of alternative mechanisms. So not as a test of, we make this distinction between tests for confounding bias and for tests of alternative mechanisms. So for their IV analysis, they need to think that Russian TV signal quality affects pro-Russian voting here through making people watch or not watch Russian news. So to put this in terms of IV, their instrument is the quality of the Russian TV signal, the news TV signal, and they have, as a treatment, they have watching whether the individual watches Russian news. And they need their exclusion restriction is basically that that the effect of Russian news TV signal quality on pro-Russian voting does not operate through something like hearing about what was on the news from your neighbors. And this same placebo population test could be seen as a way of testing whether that's the case. So you might, for the reasons we said before, you might think that the Russian TV signal quality doesn't affect whether you watch Russian TV if you are an owner of a satellite TV. So we think so that this little channel is shut down. But you might think that the channel that you measure by regressing Y on T in this tag here, which is C prime D prime, that C prime D prime might be similar to C D. So there's some strong assumptions here. The linearity is doing a lot of work here, and the additivity is doing a lot of work here. But basically, but that's the idea. And this is in fact how these authors and also how some other authors use placebo population tests to test the exclusion restriction in an IV. So they look for a population where they think the main treatment wouldn't be affected by the instrument, but the instrument might affect the outcome through some of the postulated kind of channels that the exclusion restriction rules out. And here we provide some examples. So that the Atari-Blackwell-Sen example is very similar to the one I've just talked about. And I can talk about these other ones, but I think I'm going to speed ahead because time is kind of short. And I've already said this the first key consideration. The key thing is for a placebo population test, what reason do you have to think that the key flaw or the key bias operates in the same way or similar way in the placebo population that it did in the core population? You also want to think about, do you have enough power to detect the bias? So picture that someone does a placebo population test. They say, well, I did my analysis in population 1. Now I'm going to do a placebo population test in population 2, where I don't think the treatment could affect the outcome, but some of the bias may be present. Well, but then suppose that it's just a really small sample, or a sample in which the treatment doesn't vary at all, or something like that. Well, you don't have enough power to find anything in that population. So that's something you got to pay attention to. Okay, so next, placebo outcome test. So placebo outcome test, again, we're going to alter the core analysis by changing the outcome in some way that, that will shut down the treatment effect, but maintain some kind of bias, the same basic analysis. So one kind of placebo outcome test is what's often called a balance test. And then what this is using some possible pre-treatment covariate or pre-treatment outcome as the outcome in place of the real one. So here what I'm showing here is, remember, we're concerned that Russianness is a confounder that is sort of tainting the relationship between the regression of pro-Russian voting on Russian TV signal quality, so that we're getting this A plus BC instead of just A. And so one idea is, well, you could say, okay, I have a measure that is something like Russianness, like they use percent of Russian speakers in the precinct. And then the idea here is to just use that as an outcome and say, well, I don't find an apparent effect of Russian TV signal quality on the percentage of Russian speakers. In that case, what you end up getting is B prime, and B prime is, if B prime is similar to B, then you know a lot about what this bias can be. So if you find that B prime is very close to 0, then and you think B prime is sort of similar to B, or let's say linearly related to B, then you have some reason to think that BC is not going to be very big. Right, so the question I want to ask here about placebo outcome tests. So I gave an example where someone has a concern about a confounder, Russianness, and then you come along and say, well, actually, I happen to have a measure of that. So I'll just use that as a outcome in a placebo outcome test, or otherwise known as a balance test. So the question I want to ask is, why would you use a confounder like that as a placebo outcome rather than just controlling for it? So if someone said, I'm concerned that Russianness is a confounder, and then I said, oh, I have a measure of % of Russian speakers, you might think about just controlling for it, just add it to the regression, control for it. That's another way to deal with the bias due to BC is to just to control for U, to sort of condition on U, and that will get rid of that backdoor path. So why would you do this? And forgive me here, I've used Z to refer to these things, and I don't mean Z as an instrument. So basically the point here, it's a little subtle, but stay with me. So recall from the omitted variable bias formula, the regression, the estimated treatment effect, let's say, when we omit this variable Z from the regression, is different from the estimate if we include it by the product of impact and imbalance, where impact stands for the coefficient on Z when it's included in the regression. So this means if we did include Z, what would be the coefficient on that thing? And imbalance is none other than the result of the placebo outcome test for Z. In other words, imbalance means it's the coefficient on the treatment when you regress that Z on the treatment and the other covariates. So what I'm saying here is that the result of a placebo outcome test is one component that is multiplicatively entered into this equation that tells you how much your estimate of the treatment effect would change if you controlled for that Z, if you controlled for that covariate. So one way to put this is that if you use Z as a placebo outcome, what it's testing is this one component of this omitted variable bias formula. It's just testing the imbalance part, whereas including Z in the regression checks for, in a way, it checks for both of them. It checks for imbalance times impact. So our view on this is basically that, at least mine, we're still hashing out the details here, is that if your concern is really only about Z, it does make sense in a way to just control for Z, if that's all you care about. But if what you're concerned about, if what you're wondering is, have I made the treatment orthogonal from every other possible confounder by doing whatever conditioning strategy I've done? In other words, is my treatment as if random? If what you're interested in is that proposition, is my treatment as if random, then using Z as the placebo outcome is a valid way to test that assumption of as if randomness, even if Z doesn't really have an impact on the outcome. So if Z didn't have any impact on the outcome and you controlled for it in the regression, you would find that it doesn't change your treatment effect, but that doesn't show whether Z was balanced or not. And so if what you're trying to do is see if Z and other things like Z are all balanced because you've done such a good job with your conditioning strategy, then it's sort of a more narrow and precise test to look at Z in a placebo outcome test. Because what you're interested in that case is checking balance, checking as if randomness, not just checking whether Z affects the outcome of your, we're controlling for Z affects the outcome of your regression. Okay, so and we have some examples here. I'm going to not talk about this, but we have placebo balance test. We have balance tests where it's a placebo outcome that is kind of pre-treatment covariate, and where we know that there's no way that the treatment could affect the outcome. There's other kinds of tests, and I'm just going to skip over, but look at the paper if you want, where it's not a pre-treatment placebo outcome, which comes with some complication, but it has the advantage that it can be a way of testing kind of mechanisms. That's how it seems to us. It's messier in some way, but it also allows you to kind of test mechanisms. Okay, so finally, the last category is placebo treatment test. So if you've been following along, you won't be surprised to know that what you do with the placebo treatment test is you alter the treatment in a way that that treatment won't be affecting the outcome, right? But the relationship between the treatment and the outcome is going to retain some feature of the flaw or bias that you were concerned about before. So they have a clever placebo treatment test in this paper. So what they do is, remember, the basic analysis work we have here is Russian news TV signal quality and its effect on pro-Russian voting. What they do is they take a measure of the quality of sports TV signal quality. So it's surprising to me in a way that they can distinguish between these things, but I guess it's because the antennae are different that broadcast different kinds of TV. So the idea is sports TV signal quality shouldn't affect voting. It shouldn't be that by watching Russian sports, you change your attitudes about voting. Although I would say, by the way, there have been more outlandish theories published in our journals than the idea that watching sports would affect your voting behavior. But the idea here is that watching sports TV is not going to make you more pro-Russian. But sports TV may be subject to some of the same confounders. Some of the same geographical factors would affect whether you can get signal to watch Russian football games or whatever. So the idea then is you regress the outcome on this treatment that is sort of similar to the real treatment in terms of some kind of confounder or some other flaw, but is lacking the component of the treatment that made it effective or possibly made it effective in the core analysis. This is actually, by the way, the most similar to the kind of original idea of what a placebo means in like medical studies, because we're talking about a treatment that is kind of inert, like sports TV signal quality is not supposed to affect pro-Russian voting in the same way that a kind of sugar pill shouldn't be affecting whether you have a headache. And here are some examples. There aren't as many of these, but you have some examples. A really common type actually is in RDD studies where you look at a treatment that is crossing a threshold where no policy changes. But there's other ones as well, and you can see the examples I have. And I should say, by the way, our paper, which we're about to release to the world after an embarrassingly long time, has a very big appendix with like 100 of these kind of examples. So the question I want to ask about placebo treatment test before I conclude is, when we look across these examples, but others as well, there's actually a disagreement in the literature about whether you're supposed to control for the real treatment when you do this. So should you just regress pro-Russian voting on the Russian sports TV signal, or should you control, when you do that, should you control for the news TV signal? And what you see is people really not agreeing on this. So some people doing the test without controlling, some people doing it with controlling, some people controlling for it, but saying, if this were a real placebo test, I wouldn't control for it, but I have to because they're really highly correlated. But actually, we think that probably it's the right thing in most cases, probably to control for it. Although it's more complicated than we would like. So just to give you a sense of how this works. So if you don't control for, this is using DAGs again, if you don't control for the original treatment, right? This is the original treatment, the Russian news TV signal quality. Then what you're capturing, you capture this path from T to Y, the path that goes through B prime and C. But there's also this other path that's B prime, B, and A. So it's this sort of backdoor path that goes through the actual treatment. And what you don't like about that, actually, you shouldn't like about that, is that A is actually the treatment effect, right? So we're contaminating, we're seeing if, we can put this more intuitively, actually, if you don't refer to the DAG in some way. If you look at the association between Russian sports TV signal quality and pro-Russian voting, part of that association is going to be due to the fact that sports TV signal quality and news TV signal quality are probably associated. There's probably some places have both, And so if you don't deal with that, then you're going to be picking up partly the effect of news TV signal quality on the pro-Russian voting, which is this component A. So if you do control for it, you get B prime C, but then there's this kind of attenuation factor, which is complicated. But here's what it looks like. So you get B prime C times this thing 1 minus B squared over 1 minus B prime B squared. So in a way, you could think of the unconditional test as being kind of contaminated, which would lead to false positives and low power. But the conditional test is somehow attenuated, so we might worry about low power. Um, in the end, I think, so it's not really a totally clear trade-off, and we can come up with examples where either one is sort of has better properties. But in a lot of cases, you might think that these coefficients aren't very big, b and b prime. So remember, these are standardized things. So these things are going to be between 0 and 1, and mostly not very big. At least some have argued that they wouldn't be very big in that context, at least, and especially controlling for a bunch of other stuff. So you might think that the attenuation is going to be pretty small and not to be worried about. After all, you're not trying to really estimate b prime c. You're just trying to make sure that you can tell if it's not 0. And there are some other intriguing properties, but I'll refer you to the paper if you're curious about it. And that means we really need to get it on our websites really soon. So I just want to say in closing, and then and hopefully we can have some conversation about it. What we are attracted to about placebo tests, what attracts us about it, is that we can make causal inference more scientific in the sense that it's sort of less about kind of hunches and pre-existing biases and more about sort of what does the data say. So if you think about in a seminar what kind of bad behavior a placebo test could help us deal with, one kind of bad behavior would be like the presenter comes in, presents an estimate, and says that's the answer. Thanks. Good night. Instead, what this is saying, this is saying that the author has a chance to bring up some of the possible issues with the study, and then to address them to the extent possible. And I want to emphasize there, I think it's really important that authors kind of volunteer, like make it clear for the reader, here's some things that could be going wrong. And I think one good thing about placebo tests is they should make you be specific about what the potential hazards are, what are the potential flaws or the potential risks. That kind of, I really like that real transparency, and placebo tests ideally enforce it. But it's also good for the bad behavior from the seminar audience member, which is like, oh, I don't know, I'm not really sure I buy that. Sort of kind of like aimless and sort of mushy sorts of critiques that aren't very specific. Because what we want to do is to turn those into more specific critiques. Here's a specific problem that might be present in this design, and here's a way that you could test it. So that's a better way to be addressing claims that we are making about the world with our studies. Now, but I want to emphasize there's some tricky issues. I think they're trickier issues than I expected going into this, and I think the same for my co-authors. There's also a risk we can talk about, which is what you might call null hacking, which is that just as we know, many researchers are guilty, consciously or not consciously, of massaging their analysis to get significance. Here, you could massage your analysis to get insignificance, right? So you're trying to make sure you don't reject the null hypothesis in your placebo test, and that's probably an easier task, and also probably more in demand in some way, because you've gone through all the trouble of doing the analysis, and you know that even though some reviewers now don't mind null results, there's probably not a lot of reviewers who like to see a failed placebo test. So this is a risk, and we talk about sort of how to deal with it. But one thing is that this paper is supposed to try to help us deal with it. How does it do that? Well, it's making clearer what the expectation should be in a placebo test, so that we can't sort of fudge around quite as much. I mean, it ultimately relies on researchers being honest. And finally, I think just as a basic point, I think it's important to ask when you encounter a placebo test or design one, be clear about what bias or what flaw it's meant to detect. Because I think too often, the worst placebo tests we encountered in surveying the whole literature are cases where it seems like either a reviewer just sort of thoughtlessly suggested something, or the author sort of thought it would look cool to have a placebo test, but hadn't really thought about or made clear, at least to the reader, what it's supposed to deal with. And that makes it hard for the reader to assess it and to figure out whether this is actually helping the researcher's case or not. So I'll wrap up there, and we can, and hopefully we can discuss some of these things. I'm not sure what I'm supposed to do. Okay, very good.
I have to turn off all the stuff before I get back on. Well, thank you, Andy, for that presentation. At this point, Andy Eggers is available to take questions from the audience. You can ask a question using the Zoom Q&A button that appears at the bottom of your webinar window. If you wish to be recognized and ask your question via audio, please indicate this in your Q&A text box. Otherwise, I will read your question during the Q&A period. We did have one question come in during your talk, so I'll just start with that one. From Soren Jordan. Logically, the substance of many placebo tests is that the placebo, quote unquote, doesn't do something. How do we manage a world where we're arguing for a negligible effect using a null hypothesis significance test framework that's not set up for it, especially in the world of low power?
Right. Yeah, so I think maybe Soren can clarify if this is what he means, but I think what you mean is what do we do about a placebo tests that are underpowered? That's basically what you're asking, right? So that the researcher, if the researcher is defending a research design, they want to show that there's nothing happening in the placebo test, but it could be that there's just low power, right? Is that basically the critique? I think it is.
Well, I mean, I can tell you the question I had, which was related, I think. Soren says yes, that was his question.
Good. Okay.
I would add on to that, when we do power and size analysis of some sort of estimator, we're not generally thinking of, oh, and there's also going to be this placebo test or these 8 placebo tests or whatever. And so how do we alter size and power analysis to account for the multiplicity of tests?
Yeah. Okay, yeah, so right. So first of all, I think Soren's question hits at what we think is just it's a property of placebo tests that varies across tests, which is how powerful is it, right? And I think we want to think about power here in one way that's sort of obvious, which is just like, is it very noisy? Do you have any power in the sense that you have any precision in the placebo test, such that you could detect a small, a reasonable sized association, which in this case we're hoping is due to bias. But there's also power in a test in the sense that is the test sensitive to something that you might be worried about going on in the core analysis, right? So you can have a test that's very that gets a precise estimate, but it's not sensitive to some alternative hypothesis about what's going on in the core analysis, and that can be not very powerful in that sense. And Alan just reminded me to say that I think one direction with this is to think about tests of equivalence, which is a framework that Hartman and Hidalgo wrote a nice paper about a few years ago in AJPS. So in that sense, where we reverse the kind of burden of proof, instead of saying we're going to see if we can reject the null hypothesis in the placebo test, instead to say, can we reject, the null hypothesis of no association of placebo test, to see if we can reject the null hypothesis of some substantively meaningful association in the placebo test.
I mean, my thinking would be that just like when you're doing multiple hypothesis testing with interactions or something like that, it's helpful to think of the total size and the total power of the test. So like, and that may actually give you some leeway to set, for example, higher thresholds for alpha for some of these tests, because you're considering the joint probability of these things happening.
Yeah. So for that, so we discussed this among ourselves. I think, in Alan's perspective, at least, I think I agree with him. Was that so the risk here is that someone would just show a billion placebo tests and say, well, because I'm doing a billion of them, the alpha needs to be super low in order to show that I've found anything. So in a way, it may be better to just have people report raw p-values and then let the reader make a judgment about given how many we're looking at. I don't know. I think it's an interesting question, because it's the same sorts of statistical issues about multiple comparisons, but the kind of researcher incentives might lead them to seek out multiple comparisons adjustments in this case where they wouldn't in the other cases. I'd really like to answer Anthony's question if we can. Do
Yeah, I
you
was
want me
going to
to?
say the questions are coming in thick, so I think
Yeah,
we should move
right,
on.
sure.
Presumably, a placebo test is good for at least two things: assessing bias and assessing the reliability of standard errors. You've talked about bias, but you haven't talked about
Yeah,
standard error. And so, what are your
yeah.
thoughts on that? And then also, if your main concern is a false positive, placebo tests probably don't do anything about that. What do
Yeah.
you think about that problem?
So I'll take the first one. I didn't think about the second one, yeah. So we just actually broadened our paper to, instead of defining placebo test as being about bias, we broadened it to capture the second type. Um, Hang on a sec. Sorry. Um, the reason we did that is because actually Anthony and Andy Hall have this really great, in their shark attacks paper, they do a really nice placebo test that is exactly the second type he's talking about. So what they do is they do a series of what we would call placebo population tests to check how often you would reject the null in a test where you're just comparing beach counties to non-beach counties in states where there wasn't state years where there wasn't a shark attack. So the idea there is like, it's still a placebo population test. You could imagine doing that in one state, just checking, well, would you reject the null in California in a year when there was no shark attacks. But instead of just doing it in one state, they do it like 570 state years. And so what they're doing there is that it's not a bias that they're concerned about. It's that the standard error that the way that Aiken and Bartels calculate the standard error, they think is not right. So they think that it would lead to, in doing a lot of state years where there shouldn't be any kind of effect, you'd be rejecting the null more often than you should, i.e. 0.05. And in fact, I think they reject the null something like 30% of the time in these placebo population tests. So that's why I would generalize a little bit placebo tests to say that you're looking for you want some flaw in the design, possible flaw in the design to be constant between the placebo tests and the core analysis. And in this case, it's the way the standard errors are drawn, are calculated. But in practice, what I can say about this is that there are very few tests of this type. If you look at our journals, so we don't have that many tests of this particular type. Almost every time someone says a placebo test, what they mean is a single test where you adjust one variable or change the population and you run a single test. And what you're doing is looking for bias. Very rarely are people testing standard errors, and they should do it a lot more.
I'm going to jump over to the Q&A window. So there are a lot of questions that have been asked. I'm going to try to pick a few out here in our remaining time. Roman Chowdhury asks, can you talk a little bit more about null hacking? As you mentioned, p-hacking can be unintentional. How does one approach placebo tests comprehensively but avoid null hacking?
Yeah, I mean, so the easy answer here is like pre-registration. It's tough because we're talking about observational studies. So pre-registration observational studies has some special challenges, but especially if researchers are going to be ruthlessly unethical, which we're hoping that they wouldn't be. So I think one way to approach. So I think generally the right way to do it is to be principled about the choice of placebo tests, which ones to run. So think as much as possible about what are the concerns that are in this study and how can we design tests to address them. I think another thing that is actually in favor of placebo tests, it's why it shouldn't be quite, the null hacking shouldn't be quite as bad as you might imagine, is this feature that you are minimally altering the core analysis. So you can't, if someone is in the placebo test, they like change a lot of things about the specification from the core analysis, then you should be worried about null hacking. But the fact that you're trying to make it minimally different from the core analysis, it does constrain you a little bit. I think that's one way to go. But there's no real. So a final point I think is that we as a community need to be more, just as people are now sort of recognizing that sometimes you get null results and we shouldn't disqualify people from publishing when they have a null result. We should also be probably a little bit more forgiving about placebo tests. If we're going to disqualify any paper that has a failing placebo test, we're never going to see a failing placebo test, and we'll never learn anything from placebo tests. A final thing I think is that placebo tests should more often be done as in a kind of adversarial way. What I mean by that is like Anthony and Andy's paper, where what you're doing is checking someone else's analysis rather than just showing that your stuff is okay.
Although, of course, in that case, the barrier to publication is huge if you find nothing, right? Because very often you don't want to hear, "Oh, I checked their work and they did great," right? Like, okay, thanks.
That's true.
So I'm going to ask a question that I from Michael Glick that I thought was interesting and I definitely hadn't thought of. How do you address tests where the company that owns the treatment being studied knows or can detect a placebo test is being conducted, and their knowledge of the placebo test results in them being able to indirectly manipulate testing? Have you come across this kind of situation? And to me, this is reminds me of medical testing, right? Where obviously they know how the test works; they're the ones conducting it. But I think they have protocols that sort of help them avoid the temptation to cook the results.
Okay, right. So I think this question is about, and maybe I don't know if Michael can follow up by text. But I think this question is about placebo trials, like in medicine, where you have an active and a placebo. So what I want to do is just comment on the distinction between these two things. So the problem that Michael brings up is a real issue in medical testing, where basically the double blindness of the trial is violated, and the company running the trial wants to get a certain result, and they can because they know who's getting which treatment, they can adjust things. That's not really an issue with the kind of test we're talking about. So the kind of test we're talking about is related to placebo testing through the terminology. Is related to kind of double-blind placebo and active treatment kind of trials through the terminology. But it's only kind of at that conceptual level. So we're not talking about cases where there is an active treatment and a placebo, and we're comparing these two. Because think about what we're doing. If you think about placebo treatment tests, what you're doing really in placebo treatment tests, what you've done in the core analysis is compared the active treatment to something, to the sort of control group. And then the placebo treatment is slicing up this same group of subjects in a different way. So it's some people who got the active treatment, some people who got the passive treatment. And you're making a new comparison between one group of subjects and another group of subjects. But some of the people who got what we're calling the placebo treatment versus being placebo control, some of those people would have gotten active treatment, some would have gotten control. So it's basically a placebo treatment test is a basically different thing from a sort of medical trial. What it shares is this aspect that by placebo, what we mean is that there's something inert, ideally, about the thing we're studying. And in a medical trial, we're comparing the inert thing to something active. What we're doing in a placebo test in observational studies is we're seeing what the treatment effect would be measured to be if we compare the inert treatment to no treatment, basically. And we're seeing if we would still detect something when we compare the inert to nothing, as a way of testing whether when we compare the active to nothing, we are whether we're picking up some kind of bias in that comparison.
Clara Swong asks if you can compare the placebo tests with the use of synthetic controls. Would you say that placebo tests are a big improvement? Right. What are the comparative advantages of each?
Okay, so again, I think it's fundamentally a different thing. So synthetic control is a research design for getting a treatment effect. So in synthetic control, we're taking one or a few treatment units, and we're comparing their path over time to some weighted sum of a bunch of other control units. With placebo tests, we take a research design, whatever it is, if it's synthetic control, or if it's diff and diff, or if it's an RDD, or whatever it is. We do an auxiliary analysis to check whether the assumptions behind that analysis in the first place were valid. So you could do a placebo test on a synthetic control study. And in fact, the way that they generate the standard errors for synthetic control studies, which is typically like a permutation randomization test, is closely related to a placebo treatment test, where you're basically seeing what would the treatment effect be if you pretended that some random guy was treated instead of the actual guy. So by doing that over and over again, you get a kind of null distribution and you get the p-value. That's the way that they do statistical inference in the case of synthetic control method typically. Placebo tests, but placebo tests more generally are, I emphasize that you have some research design, and then this is something that you do on top of it to check whether that research design is working or how well it's working.
Okay, I'm going to ask a question from Seth Hill. Have you thought about Rosenbaum sensitivity Rosenbaum sensitivity tests as a framework for structure? Placebo analysis could then inform beliefs about the magnitude of potential confounding.
Interesting. Right. So as I understand this question, so basically with Rosenbaum sensitivity analysis, we're thinking, how big would the confounding need to be, this hypothetical confounding factor need to be in order to change, for example, the sign of the estimated treatment effect? And I think what Seth is suggesting is, could the placebo testing be used to kind of calibrate that to say, well, and how big do we think the confounding is? I think that's right. I think that's what he's thinking. It's an interesting idea. What it seems to me is, what I don't know is how you get from the placebo test to an estimate of, like, to the kind of, to put it to the units of the Rosenbaum sensitivity analysis. I think in general, like, yes, it makes sense. But the question I have is, like, how do you map the result of a placebo test into the kind of whatever the gamma thing in Rosenbaum sensitivity analysis? But I'm curious to, Seth, if you want to follow up, or anybody follow up about how that might be done.
I mean, of course, if you knew what the confounders were, you wouldn't have to do that two-stage test. You could just control.
That's right. That's right. But let's say you had a placebo placebo population test. The idea here is that, like, you have some placebo population where you don't think the treatment has any effect. So that if there is an association between treatment and outcome in that placebo population, then you think that that's due to bias.
Right.
And if you are willing, so the tricky thing is, but maybe this is your point, Justin. If you think that the two populations are identical in terms of the way confounding operates, then again, as I said earlier, you could just subtract the bias from the placebo population, from the estimate from the core population. It's only really when you just have a kind of murky idea that these things are related, but you don't know exactly how. But it seems like in that case, you wouldn't know what to do in the sensitivity analysis either, because you don't know the sort of scale and units. That's kind of what I was trying to say before.
Yeah, I mean, it would work if you had a placebo population that was literally like exactly this, meaning it was exactly identical except for the fact that there was no treatment effect. Then it would work famously. Then
you're basically talking about a diff and diff,
Right. That's what I'm saying. Like, if you're in that situation, you don't have to do this crap anyway, because you can just sort of go right to the answer.
So it's in this murky in between area where you kind of you know pretty well what's going on, but not well enough to be able to just subtract it off.
Right. Well, we're at 1:00, and I try to be very strict about keeping to this. There are still quite a few questions, and I can pass those on to Andy, because we do have a text record of them. I want to thank Andy for being our presenter this week, and I want to remind everyone that the presentation will be posted to the website, our website, shortly after this broadcast, if you'd like to share it with a colleague or watch it again. I also want to invite you to join us next Friday, when we will host a talk by Nora Webb-Williams of the University of Illinois at Urbana-Champaign. She's giving a talk entitled, When Republicans See Red but Democrats Feel Blue, Why Labeler Characteristics Matter for Image Analysis. Please see our website, www.methods-colloquium.com, to get more information about this talk. Andy, thanks for being with us today.
Thank you.
Thanks for the audience, and I hope to see you again next week.